But look at it on the psychrometric chart just to make sure your numbers are reasonable. No? Okay.
On Dr. N's?
Sure. Yeah. Probably. We can take a look at the psychrometric chart and see if it makes sense. Okay. Now, if we go back there and we find this, where is the 50% curve, then all we would do is put this again here and go find the that EW and then replace it there, and we would get some temperature here. I don't know what it's going to be, but whatever it is, it's going to be higher. Okay. So this allows us to move us in that, and how do we connect it with the enthalpy? Well, through temperature. Turns out that if you heat air in this, let's say you have air here and you heat it, keeping constant your moisture content, then your enthalpy is increasing. And if you keep your enthalpy constant, right, and you start cooling down your air, what you do is you get a line that is like that. This is a line of approximately constant enthalpy. Well, it turns out that the air along every one of these points also has approximately the same wet bulb temperature. And this is just because air happens to have a very peculiar ratio of thermal conductivity and density and specific heat and all that, which is very fortunate for us. So the lines of constant enthalpy in this diagram are also almost exactly the same as the lines of constant wet bulb temperature. And since wet bulb temperature is the most common way of measuring the humidity of the air, it turns out it's very convenient for us to use them when we move around in these diagrams. So if we know the enthalpy here, for example, because we know this starts at 20, we heat it up to 120, for example, we can easily find the enthalpy here, the enthalpy at 120, then, right, because we know the moisture content. And then we can try to find, for example, what's the enthalpy at this point, right? So we know the enthalpy at this point, and we want to know what would be the temperature that we would need to cool that down to get a particular moisture content, or the other way around. If we cool this down to, let's say, 85 degrees Celsius, what is going to be my moisture content? And this is what happens during the drying period. During a typical drying process, the air is gaining moisture, so its moisture content is increasing, right? But its temperature is decreasing. This is on an ideal drying process in which there are no other exchanges of enthalpy. We will discuss what happens in a slightly more real process. So you could have this kind of problem where you know the enthalpy at this point has to be the same as this one, and you know the final temperature, and you need to find the moisture content. That problem is very easy to solve with this equation because your only unknown is the moisture content, right? The temperature is known, so everything here that's a function of the temperature gets replaced. Your moisture content, easy. Slightly more difficult is the opposite problem, right? Well, I want the air to get to this moisture content here. This is my target moisture content, and I want to find out what temperature that's going to happen. So again, I have my enthalpy, I have my moisture content, I need to find my temperature. It's mathematically a little bit more difficult because the temperature is not explicitable. So, oh, terrible thing, I have to use solver, right? So, but you use solver, and find T. An alternative that I have used sometimes is this one. I'm going to show you in a moment. I use a temperature. I take this temperature and make it like this. T is equal to HA minus MC over 1000 delta H0 plus Cp W V of T multiplied by T divided by Cp A of T. And so I have in Excel T here, right? So this T produces all that, and I get a new T here. You see I made this T, you see how I got this T? I took all this, put it there, HA minus all this, right? And then I took the CPA down to divide. I get a new value of T with my old value of T. Do you get how I find this T here? I only find that one. No? Yes? Maybe? Only on Mondays? You are all asleep? Okay, if I want to find this T here, and I assume the other T's don't matter too much, how do I do it? Take this H here, take all this side of the equation, and take it to subtract, and then divide by the CPA. So I take my old T, that doesn't taste very good, and put it into the equation, and calculate what T should be. It turns out that this is a convergent iteration. So this new T is going to be a better guess than my old T. So what I do is I plug it in and I let Excel iterate, and it works most of the time. So you can do that, or you can use solver, no? And say make these two guys equal. The nice thing about doing it, putting this equal to that, is that no matter what you change in the spreadsheet, it automatically changes itself. If you have to use solver, you have to do it every time. Okay, so that trick seems to work and is done many times in that spreadsheet. Spreadsheet. Okay. So this is a way of finding the temperature when you know the moisture content target and the enthalpy target. So what we are doing is moving along this line in one way or the other and trying to find at what temperature that's going to happen. Sometimes we know other information. For example, we know the enthalpy, but we don't know the moisture content or the temperature. That one's a bit more tricky. What happens when you know this enthalpy, but you don't know T or MC? How do you solve that? Of course, we can go to the spreadsheet, to the graph, and kind of get a sense of where we are. That's a good starting point, right? But the reality is that there could be many solutions to that, right? There's not like a single solution. So you need to know that there has to be some other constraint for that to be solved. However, it turns out that for every particular enthalpy, what you can be asked is, what is the wet bulb temperature closest to that one? That can be asked. What's the wet bulb temperature? And you can go to the chart and kind of get an idea of what's that wet bulb temperature. Now, if you want the spreadsheet to calculate it, again, it's not necessarily a trivial calculation. As you can see in the spreadsheet, there is a couple of tricks to do it. All right, so in the exam, you can either go and look for it, or you can use one of the tricks that's in the spreadsheet, or you can invent your own trick. I found that an easy way to guess it is that there is a bit sloppy, but there is a certain correlation between the enthalpy and the wet bulb temperatures. That gives you a good starting point. And from there, you can kind of refine it. But at least you get close to it. It's just some one of those kind of like this. No? The wet bulb temperature is equal to the natural logarithm of the enthalpy multiplied by a constant A1 plus a constant A0. all you need to do is plot those enthalpies and those wet bulb temperatures. You just pick a few enthalpies and a few wet bulb temperatures, and since we usually work in a narrow range of temperatures in the hot side, it's not so bad, right? So you can get away with it. And then what I did is from that starting point, I refine it a little bit more, right? But at least this is a, let's say, in case of emergency, break the window, kind of thing. That at least gives you an approximation. If you want something that you want to be changing regularly, if you just need a number once, maybe you pull it out of the psychrometric chart directly and it's gonna more or less work. Okay? Now, in the Excel spreadsheet, there is a method to estimate the wet bulb temperature under the assumption that you are gonna get that temperature when you move through this line at constant enthalpy until you reach saturation. So basically the assumption is that you have that enthalpy at the saturation point, right? So remember that we have already solved this issue here of finding the temperature at the saturation. So if we plug that saturation here, the MC of the saturation here, we not only get a huge, beautiful equation with which we can scare other people, but we also can solve the equation and find what is the wet bulb temperature. Because the wet bulb temperature in the saturation curve is the same as the dry bulb temperature. So here the wet bulb temperature and the dry bulb temperature are the same. Why? Because if you take saturated air and blow it through something that is wet, it won't evaporate anything because the air is saturated. So that's that situation. The water is hitchhiking in Dryer's highway and all the cars are full. That didn't win the camera, no? So all the cars are full. There's no space for the water molecules to go. Right? The air is saturated. So the wet bulb thermometer and the dry bulb thermometer are going to read exactly the same temperature. And that's why at any point on the saturation curve, the dry bulb temperature is exactly the same as the wet bulb temperature. And that's why we can plug in here these, and then put here these, and then we only have one temperature as the unknown. It's the only unknown is T. It's a huge, horrible equation with only one unknown, T. And you guys know that Solver does that beautifully. No matter what, how ugly the equation is, Solver goes and does it. It always does it, right? So imagine that. You can do it by writing a humongous equation, or you can do it by putting it, break it down into little cells that cascade into a solution. We'll do it in a moment when we deal with the spreadsheet. But I don't want to get into Excel until we understand logic. Okay, so think about that. We could replace this in there, and then we replace this with this. You see, the only unknown is T. Is T right here. The only unknown. Everything else is a whole bunch of constants. Everything else is constants. That red T is the same red T as this one, is the T as this one. The only unknown is T. This enthalpy is known because it's the same enthalpy here or here or here, and everybody here. The air in every place here will have the same wet bulb temperature. Yes?
I have just a general conceptual question for what we're doing right now.
Cool.
We're breaking this question down so that we can isolate temperature and solve for it.
Yeah.
As if it was an unknown. But when we run this printer, our temperature is one of the few things that we actually know.
Exactly.
So why is it that we're approaching this question from this angle?
Because what you want to be able to do is predict things that would happen, right? If you don't have the spray dryer here in front of you, how is it going to behave when I do this to it? What way is it going to move? It's going to go up or it's going to go down? So what we want you to do now is to look at the spray dryer as if you understand its soul, in a sense. And this is its soul. This is why it responds the way it responds. If I increase its temperature, what does it happen to it? When I change the 250 to 260, it goes up that way, right? From here to there. It does this. And then its enthalpy has increased, and when it's going to dry this way. It's going to want to go there. It's going to try to. So what is going to happen to that wet bulb temperature? And why? So what I want you guys to understand is why that wet bulb temperature down the road over there at the exit is changing. Right? This is why I'm doing this. So you know how to, basically it's like we want to manipulate this spray dryer, right? It's like you guys do with your boyfriends and girlfriends. We are learning how they function so we can make their lives happier. So, sorry. No, sorry. We were talking about manipulation. Sorry, about control. Sorry, about. Let's not go there. Can delete that part. Edit it.
It's on the record.
It's on the record. All right. So basically, understand the principles of operation, not just from an empirical point of view, but the laws that govern why the equipment responds in a particular way, right? So that's why we measure these things, so we could understand that. We have a control here, right? For example, of the temperature of the burner, which affects the input temperature, which was this one, and we could increase it or decrease it. What is the effect of that on this enthalpy? And therefore, when the drying starts to happen, how does that manifest itself here? And how that affects the wet bulb temperature at the exit? That's a very good question, Manuel. Thank you, because it gives sense to this. And the same thing happens if we try to understand, for example, after it goes out and the drying is finished, when it goes through that silver tube and climbs into the cyclone, the drying is done. It's only taking the fine particles for a ride, right? Because they are already dry. Drying happens in most of the drying happens in the cylindrical part of the spray dryer, not even in the conical part. And the rest is just dust particles being bounced around, right? And yet it cools down. So if there's no drying happening, what is happening? Well, this is happening. It's cooling down, but the moisture content is not changing anymore. So if we can understand that when we stop at a certain point, this is the behaviors that we are going to observe, then we know the impact that we should expect from the spray dryer as we just climb on the ladder and push that little button. And the same if it turns out that the moisture content changes here, up and down. What is going to change that moisture content? Well, the environment could change it, because the air from the room changes, but also the ratio of propane to air. Because when you burn the propane, you produce a little bit of water. You burn more propane, you produce more water. Turns out our spray dryer has something that is called a fixed volumetric fan. So that fan basically moves the same volume within the range that we use it. Right? So when you change the temperature, what you change is the density of the gas that you move, and therefore you change the mass flow rate of the gas, right? But the volumetric flow doesn't change much. So when you change this, because you change, if you, for example, change, well, if here in this example, I'm kind of keeping the exit temperature, but in practice, we know the exit temperature also changes. It's more like that, right? So in these three operations, for example,